Welcome to the deep dive. Today, we're diving into something pretty specific in the world of large language models, particularly LLM agents.
Right.
We're looking at how you train them for these really complex tasks, the kind that involve, say, 30 or more steps in a sequence. Think virtual environments like ALFWorld or ScienceWorld.
Yeah, and the real headache there is what's called sparse rewards,
You mean,
meaning the agent does all these actions, maybe dozens of them, this long, long sequence.
okay,
And it only finds out if it did well or poorly right at the very end. There's no feedback along the way.
so it's hard to know which of those 30 steps was the good one or the bad one.
Very hard. It's a huge credit assignment problem. Your standard reinforcement learning approaches, they really struggle to pinpoint what worked over such a long horizon.
And our sources today suggest this isn't just about slow learning. It leads to something specific they're calling an exploration-exploitation cascade failure. Sounds dramatic.
It can be in terms of training stability.
So our mission is to unpack that failure. What is it, and how does this proposed solution, Entropy-regularized Policy Optimization, or EPO, how does that actually break the cycle?
Well, to get why EPO might be needed, you first have to see why the usual methods, even robust ones using entropy regularization like PPO,
Yeah.
often fall short here.
Okay, what's missing?
They lack what you might call temporal awareness. They encourage exploration, sure, but they tend to treat step 5 the same way they treat step 25. They don't fully account for the sequence.
Got it. So let's break down this cascade failure. The sources mentioned 2 phases. What happens first? Phase 1.
Phase 1 is basically excessive early exploration because there's no reward signal coming in early on.
Right, just silence.
The standard algorithms push the agent to explore maybe too much. The entropy, the randomness just grows without check in those initial steps.
Just flailing around a bit.
You could say that. It ends up building its initial strategy on a really unstable, kind of flawed foundation because it explored blindly without any guidance.
Okay, so it starts off shaky. How does that play out later in the episode? Phase 2.
That instability doesn't just go away. It leads directly into phase 2, uncertainty propagation.
Wow.
The initial shakiness, it sort of echoes and amplifies through all the later steps. The agent's policy stays really volatile.
Oscillating, you mean?
Yeah, swinging between being maybe overconfident in a bad move and then just chaotically guessing again. So just when it should be settling on a coherent plan near the end, it's still caught in this high uncertainty loop.
So the early randomness prevents it from ever really finding a stable path later on.
That's the essence of it. Standard entropy methods just don't resolve this cycle because they aren't looking at how those first few decisions fundamentally shape the outcome 30 steps later.
Okay, that sets the stage for EPO. The idea is that entropy control needs to be smarter, needs that temporal awareness.
Right. And EPO tackles this with 3 main components that work together.
Let's walk through them. What's the first one? How does it even measure uncertainty differently?
So the first big change is trajectory-aware entropy computation. This is foundational.
Oh, wait.
Instead of just looking at the entropy, the randomness at each single step.
Like traditional RL.
EPO calculates the entropy across all the steps in an entire trajectory, an entire sequence of actions. Then it averages this over a whole batch of trajectories.
So it's looking at the randomness profile of the whole attempt, not just moment to moment.
Kind of, yeah. It captures the temporal structure. It acknowledges that the whole sequence is linked.
That makes sense. So that's the measurement. What's the second component? You mentioned something about smoothing oscillations.
Yes, the entropy smoothing regularizer. This is really key to stopping those wild swings we talked about.
How does it work?
It basically keeps a running history of the policy's entropy, like a memory of its recent stability levels. It creates a kind of safe zone based on this history.
Like guardrails.
Sort of. If the policy's current entropy tries to jump too high or drop too low compared to that historical range, it gets a nudge, a penalty, pushing it back towards stability.
So it stops the agent from exploring too blindly early on and also prevents that chaotic uncertainty later.
That's the goal. It dampens those extremes.
Okay, measurement fixed, oscillations dampened. What's the third piece? Something about adapting over time.
Right, the adaptive phase-based weighting. This uses a schedule, an exponential one, to adjust the balance between exploration and exploitation across the entire training process.
Ah, so it changes how strongly it applies the entropy control as the agent learns.
It starts off encouraging more, let's say, conservative exploration. Enough to learn, but not so much that it locks into those bad early behaviors.
Okay.
Then it moves into more balanced phase mid-training, And finally, towards the end of training, it shifts to strong stabilization to really help the agent converge reliably to a good policy.
So it's tailoring the approach based on where the agent is in its learning journey.
Precisely. It's designed to counteract the specific phases of the cascade failure as training progresses.
It sounds quite tailored. Let's talk results. Did this EPO framework actually make a difference on those tough benchmarks? Like ScienceWorld. That one involves complex experiments, right?
The results were pretty striking. On ScienceWorld, just adding EPO to a standard algorithm like PPO, well, it led to up to a 152.1% improvement in the final success rate.
Wait, over 150%? That's huge.
It is. The baseline methods often got stuck around, say, a 40% success rate after a lot of training. But the EPO versions, they converged much faster and reached success rates above 80%.
Wow, so it suggests that cascade failure really was the bottleneck.
It strongly suggests it, yes.
And what about ALFWorld, those household tasks? Similar
A
story.
similar pattern, yes. For instance, using EPO with another algorithm, GRPO, boosted the success rate by nearly 20% on certain tasks there. But the really key thing across the board wasn't just the final score, but the stability. EPO seemed to ensure the learning process didn't just collapse into chaos. It provided this monotonically decreasing entropy variance, meaning the randomness became more controlled over time, leading to smooth convergence.
Turning these really difficult, almost untrainable, sparse reward problems into something manageable.
That appears to be the effect, yes.
Okay, results like that make you want to know why it works. The ablation studies, where they remove parts of EPO, must be revealing. What happened when they took out the smoothing component?
That was very informative. On ScienceWorld, again, removing the entropy smoothing regularizer really hurt performance.
How so?
Convergence was much slower, and the success rates kind of plateaued much lower, around 50–60%. It really underscored that the smoothing is crucial for stable learning in these sparse settings. It's what breaks that cycle of oscillation between too much guessing and false certainty.
So smoothing is essential. Now, here's something that seems counterintuitive. Why did the more traditional idea explore a lot at the start of training and then gradually reduce exploration? Why did that fail here?
Yeah, that's interesting. Trying to schedule entropy decay across the whole training run didn't work as well.
Why not?
The analysis suggests it suppressed exploration too early, specifically in the initial turns of each episode, not just early in the overall training.
Okay, so at the start of every new attempt.
Right. Every time the agent started a new task run, the decay schedule was already telling it, be less random now. But the agent still needed to explore effectively in those first few critical steps. Suppressing that too soon seemed to lock it into suboptimal strategies right away for that attempt.
Triggering the uncertainty propagation later in that same episode.
Exactly. So the takeaway was, for these long, multi-turn tasks with sparse rewards, you actually need consistent, robust exploration pressure throughout the trajectory steps within an episode. A simple decay over training time isn't the right approach.
Stability at every stage of the task, not just decreasing randomness overall. Okay, one more comparison. EPO puts entropy directly into the main learning objective, the policy loss. How does that compare to methods that treat entropy more like an extra reward signal, these entropy-based advantage or EA methods?
That comparison was also quite stark. The EA methods tended to plateau, again, around that 50–60% success rate mark.
While EPO got near perfect scores, you said.
On some tasks, yes, close to 1.0. The key difference seems to be the gradient signal.
What do you mean?
EA methods add entropy as a kind of bonus reward, but that doesn't directly tell the policy how to become more exploratory if needed. There's no explicit gradient pushing it to increase entropy.
Oh, no.
EPO, by putting entropy directly in the loss function, creates a clear mathematical signal, a gradient that can actively guide the policy to explore more or less when appropriate. And crucially, the temporal smoothing ensures this direct guidance doesn't mess up the LLM's underlying reasoning abilities, which can happen with more naive modifications.
So it's a more direct, but also carefully controlled way of managing the exploration.
That seems to be the case.
Okay, so if we pull this all together, the main message is that these long-horizon, multi-turn tasks with sparse rewards, especially for LLM agents, they present this unique cascade failure problem. And standard RL entropy methods aren't equipped for it because they lack temporal awareness.
Right. They don't manage exploration effectively across the whole sequence.
And EPO addresses this head-on with its trajectory-aware calculation, the smoothing regularizer, and that adaptive weighting across training phases.
Correct. It brings stability by understanding the temporal dynamics of the problem.
Now, while EPO shows a lot of promise,
Mhm.
the sources did mention a potential area for future work, a limitation.
Yes. Regarding memory.
Right. The current EPO framework doesn't explicitly incorporate memory systems to, say, store and reuse entire successful sequences or behavioral patterns from past episodes.
Which could be very valuable. In these sparse settings, finding even one successful trajectory is hard work for the agent. Being able to remember and replay or learn more directly from that success could be powerful.
So a final thought for you, the listener. Given how valuable those rare successes are, how might future research combine this kind of stable EPO regularization with more explicit memory mechanisms? Could that unlock even faster and more robust learning for these complex agent tasks? Something to think about.